I'll get started. Are all the quizzes finished? Yeah. Okay. So this time I'll be talking about models with latent random variables, specifically variational autoencoders, because these are a convenient way of doing things. So discriminative versus generative models. Discriminative models, we've been doing a lot of work on these, whereas generative models, on the other hand, calculate the probability of a variable x or multiple kind of sets of variables x and y. So which of the following models are discriminative versus generative? This is probably an easy quiz. So let's say we have a BIOSTM part of speech tagger.
Discriminative?
Discriminative, yeah, sure. The globally normalized CRF part of speech tagger. Discriminative, yeah. And a language model. Generative. Okay. So this was an easy quiz, and I'll do a slightly harder quiz next time, just to do this. So then the slightly harder quiz is about types of variables. So for variables, we have observed versus latent variables. So observed variables are something that we can see from our data. For example, x or y. These, where x being, our input sentence and y being our part of speech tag. And latent variables are variables that we assume exist but aren't given the actual value of them. Another distinction that we can make is deterministic versus random. So deterministic variables are variables that are calculated directly according to some deterministic function and don't have any probabilistic interpretation. In contrast, random or stochastic variables obey a probability distribution and may take any of several or infinite values. So very often, when people say latent variables, they're talking about latent random variables. And I might blur that distinction here, but this distinction is rather important. In most of the models, or I think virtually all of the models that we've talked about so far haven't really been handling random variables, latent random variables. So here's the slightly harder quiz. In the attentional sequence model using maximum likelihood estimation and teacher forcing, which of the following variables are observed or latent in deterministic or random? So the input word IDs F are observed and deterministic, yes. The encoder hidden state? Latent and deterministic, yes. The attention values, A? Latent and deterministic. And then that's correct in most attentional models. And then the output word IDs are E, are observed and deterministic. So the reason why this is a little bit difficult is because the attention values, A, they kind of look like a probability distribution. You add them up, and they sum up to 1, and they're between 0 and 1, which is the characteristic of a probability distribution. But still, all we're doing with these values A, is we're using them is in part of our model to calculate the weighted sum of some values. And we're never doing anything like sampling. We're never doing anything like search and taking the argmax. So because of this, these are deterministic variables. I mentioned before there are things like hard attention where you sample these values. In that case, you're assuming there is a probabilistic interpretation where you randomly sample from this distribution. In that case, these would be considered random variables. So given that, sorry, are there any questions about that? No? Okay. So given that, we'll now talk about variational autoencoders. So why do we want latent random variables? The reason why, I think the reading materials this time were pretty good. I think they explained a semi-complicated concept relatively clearly, much more clearly than the original paper. But the motivation that it had there is we believe that there's some sort of underlying latent factor that can affect the text or images or speech that we're observing. So one example of that would be what is the content of the sentence? So we have a sentence overall, and we think there's some sort of content that we don't necessarily know how to quantify ourselves, but if we treat it as a latent variable, we can assume this. So if you also know things like topic models, how many people are familiar with topic models? To the point where you like kind of know the equations and things like that? I saw a lot of hands go down, okay. Well, so topic models assume that there's a latent topic distribution for each document. And the topics for each document are drawn from this latent topic distribution. So you can also view the topic vector of a document as a latent random variable. And there's a probabilistic interpretation of this as well. So of course you can also do that with neural nets or with variational autoencoders. Another thing is who is the writer or speaker of a sentence. So maybe sentences that I say will be very different from sentences that, for example, the president would say. For a variety of, why are you laughing? For a variety of reasons, content or other reasons. Also, what is the sentiment of a sentence? So you might say a sentence might have different sentiment. Another thing would be like what words are aligned to another in a translation. So you might assume that when you translate between sentences, some words will be aligned to others. You don't know which words are aligned to which other words. And this would be the case of something like the hard attention that I talked about before. And all of these basically have a correct answer. There's, some of these are fuzzy, like what is the content? That's a fuzzy thing. But who is the writer of the sentence? That has a correct answer. What is the sentiment of the sentence to the point where you can quantify sentiment? This has a correct answer, etc. But we just don't know what they are by looking at the sentence. So that these are the cases where we want latent random variables. So a latent variable model, this is also, we touched on this briefly in the GAN or the adversarial methods thing last time. But we have an observed output and we have a latent variable z generated from a Gaussian, and we have a function parameterized by theta that maps from z to x, where this function is a neural net. So this is from the reading. And the important intuition here, I think the reading got this across pretty well, but I'm going to rephrase it a little bit in case it wasn't clear completely from the reading. So the important thing is z here is distributed according to a Gaussian, while x is distributed according to something else that's not a Gaussian. But the important insight is we can use a neural network to take z and transform it into anything else, because neural networks can do anything, right? They're universal function approximators, so they can map from this uncomplicated Gaussian to any arbitrary function. So we want to train a model that takes these randomly sampled things and converts it into something that looks like our actual data. And we want to maximize the log likelihood of our data like this. So this is over all our training examples. And for a single example, the marginal likelihood is when you integrate over z, given the probability of z, like this. And then we can approximate this by sampling. So people, I assume, know about approximation via sampling. So if you randomly draw samples according to this probability distribution over z, if you take infinity samples, then this sum will be equal to the integral here, except that I forgot to divide by the I forgot to divide by the size of the sample set. So actually, you need 1 divided by the size of S here, and then these two things will become equivalent. So so this is kind of standard statistics or math. But the problem in this case is that straightforward sampling to approximate is problematic. And the reason why is because now we're using these big neural networks to go from Z to X, right? And calculating neural networks is expensive. So if we need to take a huge number of samples, then we'll have problems. So let's say we have our current data point up here. And this data point, of course, corresponds to some data point in the original Z distribution. But for all the other data points, we're going to have virtually no probability assigned to the correct point. So if we just randomly sample from this Z distribution over and over and over again, it's going to take a huge number of samples before we get a point that actually corresponds to giving this current data point a high probability. Is this clear? Any questions? Okay. So the solution here is the inference model. And the idea is we want to predict which latent point produced this data point. And we create this inference model Q of Z given X. And then we acquire samples from the inference model, this conditional probability for more efficient training. So basically, we take in this original X, and we predict the latent variable Z. And this is necessary for learning just about any latent variable model with a neural network. So in this example here, I'm talking about latent variable models where the latent variable is a Gaussian vector, but in NLP we have other varieties of latent variable models as well. And I'll talk about those more. So this is called the variational autoencoder. And the reason why is basically because it encodes with the inference model to get our latent variable, and then decodes with the generative model to get the actual value that we have here. So are there any questions about this? Okay. So the problem is that there's a disconnect between the samples and the objective. So we want to optimize the expectation, which is this, as I said before. But if we sample according to Q, we're actually optimizing something else. So we want to optimize the expectation according to the prior. But if we sample according to Q, we're optimizing the expectation according to samples derived from Q. So how do we resolve the disconnect? And basically the idea is our VAE objective. There were some equations in the reading. I'm not very good at math, so I like things very explicit. So to make it a little bit more explicit, basically what they did here is they take Bayes' rule. So we start out with this, and Bayes' rule, as you know, is P of Z given X is P of X given Z divided by P of Z times P of X. So it transforms like this. They did a little bit of rearranging and negating things like this. And then they used the definition of KL divergence to get something like this. If you go back, if this was not super clear in the reading, but it's a little bit more clear with this slide, then hopefully that was helpful. And so now we have the thing that we want to optimize over here. So this is our likelihood. This is the thing that we want to be optimizing. This over here is just the divergence between the true posterior of Z and or the true conditional probability of Z and QZ. We actually kind of tend to ignore this, or a lot of people discuss the VAE without discussing this, but for completeness, it's worth having here. And then the more important thing when you actually go and implement this is that you need this reconstruction or generative probability, and then the KL divergence between the two distributions. So yeah, the left side is what we want to optimize the marginal likelihood, and the right side is what we can optimize. So the expectation, according to Q, of the likelihood approximated by sampling from Q, and the penalty for when Q diverges from the prior. So you have these two things pulling in two different directions. One is pulling to learn a better generative model, and one is pulling to make sure that your inference model doesn't get too far from your prior. So this is the summary of the VAE. And by doing this, both of these you can calculate in a neural network toolkit or whatever, which means you can.
So one of the terms on the right side is the KL between the one computed by network and the prior. And on the left side, the difference is between the posterior and the same thing computed by the network. Right? So suppose you select a very simplistic prior, then you're always optimizing the lower bound. So you can potentially get a good score there, but the difference between the actual log probability of the data is going to be long, because that's the difference.
So we're assuming that Q of Z given X is a highly parameterized neural network, so it can fit Q of Z given X well, I guess.
But then if it fits P of Z given X very well, then the KL between Q of Z given X and P of Z might be very short.
Yes. That's
How does that answer?
well, so the just to rephrase a little bit. I think it's actually less important to look at the KL over here, and more important to look at the log P of X given Z in the KL term here. And basically, the log of P of X given Z will be much higher if you basically have a very informative Z every time. If every time your Z very highly identifies your data point, then the left term on the right side of this equation will become very low, which is a good thing. It means your data is very highly identifiable from your latent variable. However, what we actually want is we actually want a generative model that generates P of X. It's not just calculating conditional probability. So the KL term is basically ensuring that it still remains a good generative model, and that you're actually still optimizing the probability P of X. And it's also making sure that it doesn't send your latent variables to strange places in the space that aren't covered by the prior at all. So there's this inherent tension between these two. So if the right one gets higher, or if the loss on the right side goes down, then the loss on the left side and the right side of the equation will go up, and if this goes down, then the one over here will go up. So I don't know if that answers the question.
My only question is that if you're optimizing the lower bound,
yeah.
Can you comment about what, like, can you give any guarantees about how well you're approximating log P of X? The original thing that you want to approximate.
Can you give any guarantees? That's actually a good question. My intuitive answer is no, but that's just intuition. I don't think there are any. I don't think it's easy to bound it in the general form, because if you're assuming that these functions contain any form that you want, like most things with neural networks, it becomes very hard to prove anything. But yeah.
So they sort of motivated the use of latent variables in the fact that, say, they're writing MNIST digits, you would require to understand what digit is written, what is the orientation, what is the thickness, it seems like a fair idea that if you have a understanding of those particular terms, you will be able to better generate condition on them. But and they also go and talk about that if you start with even a random distribution, a random Gaussian, and if it is, let's say, nicely parameterized, it might, in some layers, learn all those parameters. Like you learn about orientation, about the lightness, and so on. But nobody sort of, like, they didn't sort of go back and check that whether the motivation was solved right. They never, like, inspected units which actually corresponded to a particular digit or a particular thickness level or a particular region. So it's like, while the motivation makes sense and sort of works, but did it actually pan out the way they thought it would?
That's a good question. I don't think they actually inspected that. On a similar note, there was a paper that just came out about yesterday. I don't know if you've seen this about interpretability in neural networks, where interpretable units aren't necessarily more important for a neural network than uninterpretable units. Maybe some people have seen this. There was a paper by DeepMind and Iger, I guess. But basically the idea is that they deleted various units from the network, and some of the units you can interpret them. It's like this is the cat neuron because it's on when the image is a cat. But if you delete that one or you delete any other one, you still get the same, more or less the same decrease in performance. So, I just mentioned that because you talked about whether they were discovering a single unit that corresponded to orientation or something. That might not necessarily even be a prerequisite for showing that it is doing what you want it to be. There are some interesting results about this space being better in other ways, and I'll talk about those in a little bit. Any other questions? Okay. So the other thing they talked about was the reparameterization trick. This is really important and useful for training certain varieties of VAE models, specifically ones where you have a latent vector. So the idea is basically you take this thing where you sample Z from a normal distribution, and instead of doing that, you sample epsilon from a normal distribution around 0 and 1, and then you transform this in the appropriate way to make sure that your model is end-to-end differentiable from the beginning to the end. And this is good because, as I've talked about before in like reinforce or all the other methods, anytime you're sampling inside your training process, things become unstable. So this is a good way to do this without any loss of, this is basically doing this for free. It's doing it without any loss of or any change of the actual object. So now, moving beyond the reading and moving to applications to NLP. So the first kind of application to NLP was generating from language models. So if you remember, language models themselves are generative models. They have no latent variables. They have no latent random variables, I should say. But you can still generate You can still generate sentences from them. So you start out with, or you start a while loop until you get to the end of the sentence, and then you just generate from this conditional probability every time updating your RNN or whatever else. We can also generate conditional on something, so translation, image captioning, etc. We've done all these models, sequence models before as well. And when we do this, we condition on X and generate Y like that. So the idea for applying this to applying VAEs to this approach is that the VAE-based approach is basically a conditional language model where you condition on the latent variable Z. So this is like an encoder-decoder model. So if you remember, the encoder-decoder model takes in the input and it turns it into a vector, and then it makes an output. But the latent representation, the hidden vector Z, is a random variable. So it's a variable that you can sample from. And also the input and output are identical. So the way it looks is we have sentence X. We randomly sample, or we take sentence X, we encode it, we get our latent variable Z, and then we use this to calculate the probability of the sentence X. So the motivation for latent variables, like we were just talking about, is it's possible that this could allow for a consistent latent space of sentences. And what this means, basically, is if we have a normal autoencoder, let's say we have an autoencoder that says the cat ran, and the dog walked, or something. This model can basically create latent variables anywhere in the space of, can create latent variables anywhere in the space of the numbers that its vectors can handle. In contrast to this, if we treat Z as a latent variable, and we know that Z has to be generated from a Gaussian like this, the model is basically encouraged to ensure that its latent variables are within the places where this Gaussian assigns high probability. And if you put it the other way, if you say it the other way, if there's any point in here, if there's any sentence in here, or sorry, any latent variable in here that creates a non-sentence, that creates something that doesn't actually turn into a real sentence, then this will be wasting probability, and you essentially will be losing. So you're encouraged to have all of the latent variables here within this high probability space of the prior to actually mean something. So as a result of this, this theoretically would give you a more consistent latent space where all the things in the space are real sentences. So what they did was they basically took two sentences, and then they interpolated between the vectors of these two sentences, and then tried to generate new sentences. And with the standard encoder-decoder model, I went to the store to buy some groceries, and horses are my favorite animal. And if you interpolate, you get I store to buy some groceries, I were to buy any groceries. Horses are to buy any groceries, horses are to buy any animal. And then for the VAE, they use different sentences, which seemed very unfair to me. So I don't know exactly why they use different sentences here. It seems like they probably should have used the same ones. But anyway, they interpret between them and interpolate between them, and they find that it seems to be giving better results. So I haven't gone out of my way to email the authors and ask them if they tried it on the one on the left as well. But I think it does make sense that you get more consistent results when you interpolate between these. Another thing is you could kind of view this as being potentially more robust to noise, because the VAE can be viewed as a standard model plus some regularization, because you're randomly sampling from latent variables. So there's that as well. We have some example code. It's pretty simple, but if you want an example of how to do the reparameterization trick, etc., you can use this in that way. So so yeah, I guess one other good thing here is that unlike a normal encoder-decoder, so in normal encoder-decoders, you can get vector representations from the, you can get vector representations after the encoder is done, but you actually can't easily sample from these models as well. So you can't easily get samples. So you have language models that you can sample from, but don't give you a vector representation of the sentence. you have encoder-decoders, which you can get a vector representation of the sentence, but you can't sample from them. While for VAEs, you can get a vector representation of the sentence and sample from them. So that's another advantage. Okay. Are there any questions? Okay. So this was a pretty straightforward application, but actually applying VAEs to text is harder in many ways than applying them to images, for example. And one of the reasons why is of the two components in the VAE objective, the KL divergence term is much easier to learn. And what I mean by this is basically if you have a KL, if you have the VAE that's generating your mean and variance for every point, and then sampling your z from this value, how would you best optimize the KL divergence term here? Like you're calculating the KL divergence between this and the normal distribution where your mean is 0 and your covariance is identical. So if two functions are the same, this is your prior, and this is your Q posterior. So how would we minimize the KL divergence between these two?
Can we make them the same?
Yes. It's not a trick question. You make mu 0, and you make this the identity matrix. So it's basically trivial to minimize the KL divergence term. And the only reason why this doesn't happen is because if you have z can be informative and basically improve your likelihood. So on the left side, on the other hand, this requires a good generative model. And this requires a model that can actually lower the log likelihood. So at the very beginning of training, this you can set down to 0 immediately. And then you need to go in and train your language model, basically, or your decoder, to get good results. So what happens here, basically, is immediately this goes to 0. Or this goes to this value over here, and your decoder learns to ignore z entirely. So as a result, it becomes very difficult to train these. So there are a couple solutions to this. One solution is KL divergence annealing. This is really important in variational autoencoder models of text. So the basic idea is you multiply the KL term by a constant value lambda starting at 0, then gradually increase it to, I say increase it to 1 here, but sometimes if you increase it to 1, that also causes problems. So then you stop it at 0.2 or something. But if you stop it at 0.2, it's not a real variational autoencoder, so you have trouble adjusting this as a hyperparameter. As a result, the model can learn to use z before getting penalized. So what it looks like is basically you start with your KL term weight very low, and the model learns to use z and use very kind of diverse z values. But then you start introducing the KL divergence term, and then suddenly, the moment you start penalizing KL divergence, the KL divergence goes down a bit, but it doesn't go down all the way to 0. So you still are able to use your latent variables. So this is a pain, modifying this annealing schedule. So another solution that people have used is to weaken the decoder. So even if you do this KL divergence annealing, it's theoretically still problematic. And you can actually show by going through the math appropriately that the optimal strategy is to ignore z when it's not very useful. So the reason why Z is not very useful in generative models of text that use these is because the generative model of text is a recurrent neural network. And recurrent neural networks are very strong generative models anyway. We can make very good language models with a recurrent neural network without even having any latent variables. So as a result, the solution to this is to weaken, or one solution to this is basically to weaken the decoder X, P of X given Z, so that using Z is essential to get a good probability here. So one example of this is to use word dropout. So word dropout basically occasionally skips inputting the previous word into X. So what this means is if you don't have the information about the sentence stored in Z, you're going to pay a penalty because you lose some of your context and aren't able to base your next decisions on this. And another example is to use a convolutional decoder with a limited context. So in other words, this is kind of like using an n-gram model instead of a recurrent neural network language model. So it's only looking at very limited context. So if you do this, then Z will have to store information about the entire sentence in order for you to get good scores. So these two things make doing VAEs a little bit annoying, but if you want generative models, then within the neural network framework, they can still be very useful. Are there any questions so far? Okay. So now perhaps the more interesting part from an NLP perspective, because this is the previous one was kind of just an application of the stuff in the reading that applied to images to NLP. Now this becomes something that's kind of very, I wouldn't say unique to NLP, but something that seems very NLP-ish and wasn't covered in the reading at all. So here, now we want to do discrete latent variables, discrete random variables. And what do we mean by discrete latent variables? So many variables are better treated as discrete. For example, the part of speech of a word or the class of a question or speaker traits or whatever else. So instead of having a vector that treats these kind of in a fuzzy way in continuous space, you might want these to be made very explicit. And you can do this by having your variables be discrete. So how do we handle these? I've already talked about a bunch of different ways to train models. The easiest one is enumeration. So for discrete variables, our integral can be treated as a sum. And if this sum, the thing that we're summing over, it has a small enough class, we can just sum over all of our possible options. If this is something that you can do computationally, I highly recommend doing this. If you have 5 options, you should not be doing reinforcement learning and sampling. You should just sum over all of them and get your results, because this will be far, far more stable to do it this way. Now, if you can't do that, if you can't get enough, if you can't get enumerate over all of them, you can randomly sample a subset of the configurations and optimize with respect to the subset. So these have a number of flavors. Both marginal likelihood and minimum risk and reinforcement learning have been covered in previous classes. And the problem is you cannot backpropagate through the sampling, resulting in very high variance. So an interesting trick that can be very useful in these cases is there are reparameterization tricks that can be applied to discrete variables as well, much like the one that they used for continuous variables. So I will explain this in a moment after I restore. So the idea here is that we don't want to be sampling inside of our network. We want to be sampling outside of our network where we're not blocking the gradient flow, but we can still do something similar to sampling to try to approximate what we, the values that we want. So the way we do this is if we look at our original method for doing categorical sampling, we take x, the probability of z given x, where z is a discrete variable, and we sample according to its probability. So the way we do this in a reparameterized version is something like this. So these two equations are exactly equivalent. So the first equation and the second equation will get samples from exactly the same distribution. And the way this works is we have our vector of log probabilities, like negative 1, negative 0.5, negative 2, etc. And normally for the categorical sampling, we would convert these into probabilities and then we just sample over it. But it turns out there's a distribution called the Gumbel distribution where you sample things like negative 0.2, negative 0.8, negative 0.3, and you add these together. And then if you take the max of this sum, the distribution that the maxes will follow is exactly the same as the distribution that the original categorical samples would follow. And the Gumbel distribution, I might be getting this wrong, but it's something like I think that's right. Maybe. But basically, if you sample according to this distribution, then it has this nice property. So this is good, but this is still making a discrete decision, right? We have the argmax in our neural network, and having an argmax in your neural network is a no-no if you want to backpropagate through it. Oh, I actually had that on the slide. Good thing I got it correct. Otherwise, I'd be very embarrassed. But still, the backprop is not possible due to the argmax. So the idea is to use something called the Gumbel-Softmax, and it's a way to soften the decision and allow for continuous gradient. So simply, instead of the argmax, you take the softmax with a temperature parameter. So we've seen this kind of temperature parameter before. Just in case you've forgotten what this does, basically it makes a distribution more or less peaky. So if we set this temperature to infinity, we get a completely flat distribution. If we set this temperature to 0, we get a perfectly spiky distribution. So what this looks like is we have our categorical distribution here, and we have that expectation over the various discrete classes, and then we randomly sample one, basically. And if we randomly sample one, then of course we get, we'll get one of the values there. Now, if we do the Gumbel-Softmax trick and take our temperature to be equal to 0.1, we'll get something that looks very similar. It's very close to a one-hot vector, where the highest scoring value gets most of the weight between 0 and 1. Then as we gradually increase the temperature, it makes things more flat until we get to something that looks a lot like a uniform distribution. So the idea here is if you start out with a very high temperature and then gradually decrease it, you can start out with something that's kind of continuous and highly differentiable that spreads your weight over a lot of different parts. Then you gradually decrease and decrease until you approach something that looks like the actual categorical distribution, and then you're sampling from this, which gives you the correct distribution over your latent variables. So this is a really nice trick because it, despite the fact that discrete variables are not differentiable, this allows you to move them into a differentiable space. So are there any questions here? Yeah.
So do you decrease the temperature param over training, or?
Yes. Yeah, overtraining. And you need an annealing schedule for this. It's another hyperparameter to your model. But yeah, unfortunately, when you want to do interesting things, the number of hyperparameters tends to increase. Anything else? Okay. So now I'll move on to a couple of examples of applications of variational autoencoders in natural language processing. So the first one here is variational models of language processing. This was one of the early papers on VAEs for language, so it's kind of a little bit not focused. It's not focused on a single thing, but it has various things. But this was a variational model for document modeling, and the variational model for document modeling was basically, like I said before, topic models are one example of a model that used latent variables for documents. And the idea here is that they're basically doing the same thing. They have a latent variable that describes the content of the document. But it's not, it's a latent continuous variable as opposed to a latent discrete variable. Then they had another similar one for question-answer selection. So they would encode the question in this latent space and then use this to do question answering. This one I wasn't entirely convinced that it needed to be a latent variable model, but they seem to show that it worked better, and I think that might be because of the regularization effect. Yeah, so yeah, what I said there. Then there are perhaps, this is a perhaps more interesting, more of a twist on the latent variable models. So this paper is called Controllable Text Generation, or Towards Controllable Generation of Text, or something like that. And what it does is it creates a latent code Z for content and another latent code C for various aspects that we would like to control, including sentiment. So the idea is you have your X, you have your encoder, and from the encoder you predict Z and C, which are kind of two aspects of the sentence, and then C is the latent code for various aspects like sentiment, and they have a discriminator that basically would like to predict the or that forces the C to be handling this thing by using it to predict sentiment. I realized that this graph doesn't match with how I remembered the paper, so I won't over speak based on how I remember the paper. But the basic idea is that you have a discriminator that allows you to separate the content in the style by discriminating, either to improve the chance of predicting the style from C or decrease the chance of predicting the style from Z. And these are both continuous variables. So they have a few interesting results on this where they then go and modify C to be more like positive sentiment or negative sentiment, and you can generate positive or negative sentiment sentences. So we also have a paper that's that mixes continuous and discrete latent variables. So if you want to use both continuous and discrete latent variables in a sequence model, for example, you want to take in a sentence of a particular sentiment and output a sentence of a different sentiment, then this is a model that would allow you to do this with specific discrete tags. So this is done also with a variational autoencoder framework, and it has an encoder-decoder objective. Specifically in the experiments here, we used it for inflecting words. So the idea is you have a word words, and it has a latent continuous lemma that basically expresses the content, and then you have latent binary variables that express its morphological inflection. And the way we optimize this is by using the Re-parameterization trick for the lemma, and then using Gumbel-Softmax or Gumbel straight through for the latent binary decisions here. So these are good if you want to use latent variables that have a fixed form, like tags or fixed size vector. But you can also use latent variables that are symbol sequences of variable length. So if you have an encoder-decoder, the idea here is that you have your encoder S, and then you have a latent sequence C in the middle, and then you want to decode S one more time. So now instead of having a single vector between your inference model, and your output model, you now have a sequence of discrete symbols. So why is this useful? The method that they used in this example was summarization. So they had a model where basically what you would do is you would try to generate a sequence in the middle that you could then use to decode the output without losing information in a way. So this model only had the ability to copy words from the source sentence. So basically, it can do things like delete words that aren't very informative and then restore them in its decoding stage. So that means you could do things like delete the, or compress a longer expression like it would be good to into should or something like that. And you could still reproduce the original sentence. So then the way you train this is basically there's no easy Gumbel Re-parameterization trick or something like that for sequences because the length varies depending on the length of the sequence. So what they did here is they simply used the reinforce algorithm. And if you have the reinforce algorithm, if you use reinforcement learning algorithms, you don't have to worry about the sequence being differentiable, and you can just optimize anything you want. As I said before, reinforce is extremely unstable. So if you have a big action space, it's not easy to optimize these models. So what they did here is they limited to only copying words. And if you only copy words, then your action space only becomes the words in the original source sentence. That is why they were able to optimize this with any sort of accuracy. Yeah?
If you're only copying words, then how can you convert A to B to English?
Oh, you can't actually. This model isn't super widely used for summarization, and I think perhaps it's the reason why. It can only do extractive summarization, not abstractive summarization. So there's also some interesting attempts to discover language. So the idea here is you have a picture here of a person holding a deep learning textbook or something like that, and you try to turn it into a sequence of latent variables, and after that, you have 3 images where one is a person holding a flower, and one is a person holding the deep learning textbook, etc. And then on the output side, the decoder has to choose which one of these is correct. So you have these discrete symbols here, and it has to basically solve this game by using only the discrete symbols. So the idea is that the discrete symbols become a language with which 2 computers can communicate. And then this doesn't really work that well. And there was a paper that basically tried to make this language look as close as possible to what a human language actually looks like, and they had to add all these tricks in order to make it work well. But despite the fact some journalists, maybe some of you remember this, got a hold of the story and said Facebook is training robots to communicate with each other in a language that we don't understand. But they were forced to shut it down or something like that. That was talking about this work very similar to this. And it shows you how things can get out of control. Because it really is basically as simple as this. It's learning a sequence of discrete symbols not very well, and they shut it down because it wasn't working very well. And now suddenly it's an existential threat to the human race. Okay, so there's also methods to handle latent variables in recurrent models. There's a bunch of different methods to do this. This is just one example of them. There might be more straightforward ways of doing this as well, but basically what they do is they have a prior that generates the next latent variable based on the previous hidden state. Then based on the previous hidden state and this latent variable, they generate the observation. And then based on all of these, they choose the next hidden state. So it's a model like this. Then they have the inference model. And the inference model is allowed to look ahead at the next symbol that they're generating. So if you're interested in implementing this, you can read the paper. It's not super complicated, but just so you know, if you want latent variables in your recurrent neural network, you can use them as well. So that's actually shorter than I thought, but I'm done with the content that I had for today. Are there any questions about these or discussion? Just to give a final thing. So, like, why would you be interested in using this in this work? Let's say you really like Chomsky or something like that, and you think there's this generative grammar in our mind that determines how we learn how to speak language. You could assume that that's a latent variable, and you want to discover that latent variable that corresponds to how we speak language. Or maybe there's some parameters of our language that determine how our language works or something. Nobody has really done that, or nobody has done that well anyway. But I want to point out that we're not limited to little vectors full of continuous variables. These latent variables can be anything you want them to be, although it will make inference harder. So if you like generative models, you think you want to create a good generative model of text, something like a VAE type model would be a good way to do that. So if you want to discuss more, I'll be happy to discuss more. So, okay, thanks everyone.